Let's wait for a couple of minutes for more participants to join. After that, we will start. Let's wait for a few minutes more. Let's wait for some more participants to join. After that, we will start. Okay, so we may start now. So, in the last NPTEL lecture, in the last NPTEL session, I discussed some problems related to laterally loaded files, and today I'm going to discuss some problems related to laterally loaded files as well, and uplift capacity of files. So today is our ninth NPTEL live session of Advanced Foundation Engineering course. And let me reintroduce myself once again. My name is sinjandebnath. I am a PhD student in the Department of Civil Engineering at IIT Kharagpur. So let's get started. Please let me know if you can see my screen or not. So let's go to the first problem. So this is the first problem. Determine the lateral deformation at the top of a solid free-headed pile. So we need to determine the lateral deformation at the top of a solid free-headed pile subjected to a horizontal load of 100 kilonewton at the top of the pile. So basically what is happening over here is that we need to determine the lateral deformation at the top of a free-headed pile. Okay, so a horizontal load of 100 kilonewton is acting on top of the pile, and we need to find out the corresponding deformation, the lateral deformation at the top. Okay, so we need to use the Hetany approach. We need to use Hetany approach, and we have been asked to model the pile as finite beam. Okay, finite beam. So actually in Hetany approach, there are two types of approaches. One is was in one approach beam the well in Hetany approach. First of all, in Hetany approach, the pile is considered to be a beam. Okay, and it is a Hetany approach is an analytical solution where the pile is considered to be is considered as a beam. Okay, so if the pile is very long, if the pile is very long, it is modeled as a semi-infinite beam, and if the pile is short, it is modeled as finite beam. Okay, uh, the diameter and the length of the pile is given over here. The diameter of the pile is 0.5 meter and the length of the pile is 3.3 meter respectively. Kh is the horizontal subgrade uh, modulus. Okay, it is constant with depth. And one thing I must mention, that in Hetany approach, the modulus, that is the subgrid modulus, it is the horizontal subgrid modulus, it is constant with depth. Okay, in Hetany approach, it is constant with depth. And EPIP of the pile is, EP is the Young's modulus or modulus of elasticity, and IP is the moment of inertia. So EPIP is, which is also known as the flexural rigidity. It is 45,000 kilonewton meter square, and the value of kh, that is the horizontal subgrade modulus, it is 50,000 kilonewton meter square per meter, and all the other coefficients at z by l equal to 0. Z means the depth from the ground surface, and l is the length of the pile. All these coefficients are given. This the values of all the coefficients are given in the question, and it can also be determined using a chart, which I will also show later on. So so first of all, let me discuss about Hetany's approach. Well, in the NPTEL lecture, you can also find out about the Hetany approach, and I will just brief the concept once again. So Hetany approach. So Hetany approach. So what I'm going to do is that I'm going to first brief. I'm going to first of all I'm going to talk about Hetany approach. I will just uh, give you a brief summary of Hetany approach. So what is Hetany approach? In Hetany approach, the pile is modeled as a beam. Okay. In Hetany approach, pile is modeled as a beam, and we know a pile can be long or short. Okay, so a long pile is modeled as a semi-infinite beam. and short pile is modeled as a finite beam. Semi-infinite beam means the depth is at a much greater depth. Okay, and finite beam means the depth is not very long. The depth of the pile is short. Okay, so short pile is modeled as a finite beam, and long pile is modeled as a semi-infinite beam. Okay, so let me go back to the question once again. So it is also free-headed pile. Okay, a free-headed pile, and a horizontal load of 100 kilonewton is acting at top of the pile, and we need to find out the corresponding deformation of the pile. Okay, of the pile head. So first of all, let me write down the data over here, all the information that are given in the question. So the horizontal load that is acting at top of the pile, H is 100 kilonewton. Okay, so and also the diameter and length of the pile. The diameter is how much? It is 0.5 meter, and length of the pile is 3.3 meter. Okay, and KH is constant with depth. EPIP, that is the flexural rigidity. EPIP is how much? It is 45,000 kilonewton meter square. And KH is the horizontal subgrade modulus. It is how much? It is 50,000 kilonewton meter square per kilonewton per meter square per meter. Okay, and then the values of coefficients I am not writing now. I will refer to them later on. So these are all the data that are given in the question. Okay, so Hetany approach. So Hetany approach. In the question, it is a free-headed pile subjected to a horizontal load. Okay, so for a free-headed pile, the corresponding deformation can be given as, according to Hetany, it is y, that is the deflection, it is 2 into h into lambda divided by kh d and k rho h. This, okay. So what is lambda? Lambda is equal to root 4 kh d by 4 ep ip. Okay, so first of all, we need to calculate lambda. Okay, so let us calculate lambda first. So lambda is equal to root 4. Kh is how much? That is the subgrade modulus. It is how much? It is 50,000, right? It is 50,000. And the diameter of the pile, what is the diameter of the pile? It is 0.5 meter. So it is 0.5 divided by 4 EPIP. So what is the value of flexural rigidity? It is 45,000. So 4 into 45,000. Okay. So if you calculate this, you will get lambda to be 0.61 per meter. Okay, 0.61 meter inverse. So this is the value of lambda. Okay, so now we know the value of h. H is the horizontal force that is acting on the top of the pile. We know the value of lambda. We know kh. We know the value of d, which is the diameter of the pile. We need to find out this. This is the coefficient. Okay, k rho h. For z, z is the depth. So for z by l equal to 0, this k rho h is given. This is the k rho h. It is 1.1376. Okay, So k rho h is, it is the coefficient for z by l equal to 0. It is 1.1376. So what is z by l equal to 0? See, z means the depth, okay? The current depth that we are considering from the ground surface. So that is the depth. So load is acting on top of the uh, pile, or at the pile head. So where is the pile head? It is at the ground surface. Okay. So we need to find out the corresponding deformation of the pile head, which is at the ground surface. So in this case z by l, so in this case, what is the depth? It is 0, obviously. So we need to consider the depth 0, because we need to find out the deformation at the ground surface. Okay, so z by l is equal to 0. And if you look at these charts, okay, see, z by l equal to 0. Okay, and how much is our lambda? Lambda is 0.61. Okay, and in this chart, see, we need to find out lambda l. Okay, so how much is lambda l? Lambda l is how much? Lambda l is 0.61. And what is the length of the pile? The length of the pile is 3.3 meter. So length of the pile is 3.3 meter, and this will come out to be, lambda l comes out to be 2, around 2. Okay, it is around 2. So if we look at this chart, okay, lambda l is equal to 2 and z by l 0. These are the corresponding coefficients. You see, k rho h is 1.1376. 1.1376. It is already given in the question, and it is coming from this chart. Okay, and it is given in Paulus and Davis 1980. In this paper, the chart is given. Okay, so this is how the coefficients are coming. Okay, you can refer to this chart also. From this chart, you can find out the values of these coefficients. Okay, k rho h, k theta h, k rho m, all these coefficients. Okay, so uh, where are we? So lambda l is equal to 2. Fine. In the next step, we need to find out how much is the deformation, lateral deformation. Okay, so what is the formula? I have already written over here. So 2h lambda by khd, and the coefficient multiplied by the coefficient, so which is k rho h. So now we have the values of all the parameters with us. So now let us just write the equation once again and put all the values of all the parameters into that equation. So what is the equation? Y is equal to how much? It is 2h lambda divided by kht, and the coefficient is k rho h. Okay, so now let us just put the values of all the parameters into this equation. So what is the value of h? That is the horizontal load. It is 100 kilonewton. Okay, so 2 into 100 kilonewton. What is the value of lambda that we have calculated? It is 0.61. How much is the value of kh? That is the horizontal subgrade modulus. It is given in the question. It is 50,000 kilonewton. 50,000 kilonewton per meter square per meter, or you can say it is 50,000 kilonewton per meter cube. Okay, so it is 50,000 into d. How much is the diameter of the pile? The diameter of the pile is 0.5 meter. Okay, and what is k rho h? The value of k rho h, which we have already found out from the chart, and it is also given in the question. So it is k rho h is how much? It is 1.1376. So k rho h 1.1376. Okay. So now if you calculate this, you will get the value of y to be 5.55 millimeters. So this is the lateral deflection, okay, corresponding to 100 kilonewton, which is acting at top of the head. This is the lateral deformation of the pile head. Okay, so please let me know if you have understood or not. Please go through this problem. Please go through this problem once. I'll resume this session after 5 minutes. So I hope you have all gone through the problem. If you have any doubts, you can let me know, or you can let me know via email, or you can write in the discussion forum. So uh, let me go to the next problem. So let me see what is the next problem. So the next problem is determine the lateral deformation at the pile top in question number 1 if the pile is a fixed headed pile. So in this question, the pile is a fixed headed pile. Okay, the question is similar to the previous one. In the previous question, the pile was a free headed pile, and in this particular question, all the data are same, but the pile is a fixed headed pile. Okay, so generally what happens is that in case of a fixed headed pile, see, you have a free-headed pile, okay? You are applying a load on top of the pile, and that is on the pile head, and it is deforming, okay? The pile head is deforming, okay? And in case of a fixed-headed pile, what happens is that you are trying to restrict. You are actually trying to restrict the movement of the top of the pile, okay? So due to this, you are applying a fixity at the top of the pile, okay? So, due to which, suppose after applying the fixity on top of the pile using a pile cap, and after that, if you are trying to applying a if you are trying to apply a horizontal load on top of the pile cap, it will try to deform laterally. But the pile cap, which is trying to restrict the movement, will also give a counteracting moment, okay, to counteract the lateral deformation of the pile top. Okay, so basically it will try to, so basically in case of fixed headed pile, the pile cap will provide a counteracting moment which will try to counteract the lateral deformation which is being caused due to the horizontal load. Okay, so in that case, uh, so let me show you how. There is a special process which we need to follow in order to solve this type of problems using Heteny's approach. Okay, so uh, see, let me solve this problem, and I will explain you as I solve this problem. Okay, uh, so first of all, we need to find out. Okay, so first of all, we need to find out the free-headed deflection. So first of all, let us consider that there is no fixity on top of the pile. The top of the pile is a free-headed pile. Okay, forget about the fixity. Okay, first of all, you consider that the pile is a free-headed pile. Okay, so we need to find out the corresponding deflection of the pile head. Okay, so we need to find out the free-headed. We need to find out the deflection of the free-headed pile like we did in the earlier questions. In the similar way, you need to find out the free-headed deflection of the pile head. Okay, so that exactly we have done in the previous question. Okay, in the previous question, the pile was a free-headed pile, and we have found out the lateral deflection of the pile head. Okay, using this particular formula equation. So we need to now in this question the pile is fixed headed, so in this type of question we need to first find out the deflection. Okay, lateral deflection of the pile head, the pile head by considering the pile to be a free headed pile. So what is the lateral deflection of the free-headed pile of the pile head? Considering the pile is a free-headed pile, we have already determined it is 5.55 millimeter using this equation. Okay, so it is 5.55 millimeter. So now what is happening is that now let us consider the pile to be fixed headed. Okay, forget about free headed now. So in case of fixed headed pile, you have a pile cap on top of the pile. You have like this. Suppose this one is your pile and there is a pile cap on top of the pile. Okay, so the top of the pile is restricting, is will try to restrict the lateral movement of the pile head. Okay, this is the pile head, pile head, and this is the pile cap. This cap will try to restrict the lateral deformation of the pile head. So you are applying a load, horizontal load in this direction, and the cap will try to restrict the lateral deformation. So in order to restrict the lateral deformation, the cap will provide a counteracting moment. Okay, it will provide a counteracting moment, and this moment will try to counteract the lateral deformation of the pile head. Okay, so this uh, moment due to fixity is defined as m0. Okay, so m0. So what we need to do is that in order to find out the net deflection due to h, in order to find out the net deflection due to horizontal load h, we need to just, what we need to do is that we need to find out the net deflection. By how? First of all, we need to consider this pile to be a free-headed pile. We need to first find out the free-headed deflection of the pile head, and after that we need to apply a fixity on top of the pile, and using the counteracting moment m0, we need to find out the corresponding counteracting deflection, deflection due to m0 moment. That is the deflection caused at the pile head due to m0 moment. Okay, after finding out both the deflection, we need to just subtract the deflection due to m0 from the free headed deflection. Okay, that net deflection is the lateral deformation of the fixed headed pile cap. I hope you have understood. I will show it. I will show you how to do that. Okay, so m0 is the counteracting moment. Okay, so first of all we need to find out the amount of counteracting moment. Okay, so m0, that is the moment due to fixity, and here the fixity is the pile cap. Okay, it is trying to it is trying to counteract the lateral deformation due to h, horizontal load h. Okay, so m0 is how much? It is given by h by 2 lambda k theta h by k theta m at z equal to 0. This one is also at z equal to 0. Okay, so we need to find out first what is the value of k theta h and k theta m for z is equal to 0, and we know lambda l, and we know the lambda l of this pile. Okay, so lambda l is how much? Lambda l we have found out already, it is around 2. Okay, so corresponding to 2 and zyl is equal to 0, we need the value of this, that is the k theta h and k theta m. Okay, so k theta h is around 1.1341 and k theta m is around 1.0762. Okay, so we need to put this value and this value into this equation. So h is how much? H is 100 kilonewton. H is 100 kilonewton by 2 into lambda. Lambda is how much? We have already determined. It is 0.61 meter. So it is 0.61 meter. K theta h we have already determined from this chart. K theta h is 1.1341 and K theta m is 1.0762. So let me write it down over here. So k theta is 1.1341 and k theta m is around 1.0762. Now, if you calculate this, you will get the value of m0. So m0 is how much? M0 comes out to be 86.4 kilonewton meter. Okay, so m0, that is the moment due to fixity, is around 86.4 kilonewton meter. And now we need to find out the corresponding deflection due to this counteracting moment m0. Okay, so y, that is due to m0. We need to find out that. So what is the equation for that? So for that, the equation is two into m0 by kHd lambda square k rho m. You can find out the details of these equations in the NPTEL lecture series by Professor Deb. Okay. So now we need to just incorporate the values of all the parameters into this equation. So let me see what we know. We know the value of m0 we have already determined. So what is m0? M0 is 86.4. So 2 into 86.4. Kh is how much? Kh is the horizontal subgrade modulus. Kh is 50,000, which is given in the first question. So Kh is 50,000. The diameter of the pile is 0.5 meter. And what is lambda square? Lambda is 0.61 meter inverse. We have already determined in the first question. 0.61 inverse. And what is k rho m? K rho m is the coefficient which you can find out from this chart. So k rho m for lambda L is equal to 2 and z by L is equal to 0. K rho m is this minus 1.0762. So it is minus 1.0762. Now, if we calculate this, y will come out to be minus 2.77 millimeters. Okay. So now we need to find out the net deflection. Okay. So what is the net deflection? We need to subtract the deflection, the free-headed deflection. Uh, we need to subtract the deflection due to m0, that is the due to counteracting moment from the free-headed deflection. Okay, so it will give the net deflection. So what is the free-headed deflection? The free-headed deflection is 5.55 millimeter. 5.55 millimeter minus y. We will take the magnitude only. So the magnitude of deflection is 2.77 millimeter. So it is 2.77 millimeter. Okay, and it will come out to be 2.78 millimeter. Okay, so this is the net deflection. Net deflection of the pile head, fixed headed. Okay, see the direction of the deflection. Okay, the sign. The free-headed deflection is positive because it will try to deflect in the positive direction, that is in this direction. That is, it will try to deflect in this direction. This direction is positive if this is the pile, and if this is the pile, and after deflection it will be like the pile head will deflect like this. The pile will deflect like this in case of a free-headed pile. So if this direction is positive, the deflection is that is why the deflection is in positive. Okay, it is 5.55 meter positive, and you see the counteracting moment, and this deformation, this deflection will be counteracted by a counteracting moment in case of a fixed headed pile. So in that case, the deflection, the moment will try to deflect in opposite direction. Okay, like this. So it will try to deflect the pile head in opposite direction due to horizontal load H. So a counteracting moment will act and it will try to deflect the pile head in the opposite direction. So that is why the sign of the deflection due to counteracting moment is negative. Okay, it is in negative direction opposite to that of the fixed headed pile, opposite to that of the free headed pile. Okay, so that is all. So please go through this problem. I will continue after 5 minutes. Okay, so I hope you have all understood this problem. And if you have any doubts, you can uh, mail me personally. You can find my mail address in the mm, find my mail address in the YouTube description section. In the description section of the YouTube video, you can find my email address. You can mail me, and also you can write down your doubts in the YouTube comments in the chat box, and also you can write down your doubts in the discussion forum of NPTEL. Okay, so let me proceed to the next question. So, this is third question. So here, let me read out the question once. A pile of diameter 0.5 meter and length 20 meter is installed in a clay soil. The undrained question value of soil is 100 kPa. The adhesion factor is 0.4. Determine the gross uplift capacity of the pile. Okay, so uplift capacity. The unit weight of the concrete and soil is given 24 kilonewton per meter cube and 20 kilonewton per meter cube respectively. So we need to find out the uplift capacity of the pile which is embedded in a installed in a clay soil. Okay. So first of all, let me write down the information or the first of all let me write down all the data that are given in this question. After that, I will explain what is uplift capacity. Okay, so the diameter of the pile is 0.5 meter. The length of the pile is 20 meter. It is installed in a clay soil. The undrained question value is 100 kPa and the adhesion factor alpha is 0.4. Okay. So we need to find out the gross uplift capacity of the pile. The unit weight of concrete is 24 kilonewton per meter cube and the unit weight of soil is 20 kilonewton per meter cube. Okay. So what is the uplift capacity? Let me just present you a brief of the uplift capacity. So uplift capacity. So what is uplift? Uplift is actually pulling out. Okay. Uh, so uplift means pulling out. So uplift capacity of pile means how much load it is required to pull out a pile. Okay. To pull out an installed pile. A pile which is already embedded into the soil, how much load is required to pull out that pile. Okay, it is the uplift capacity of that particular pile. Okay, the load that is required to pull out a particular pile from a particular embedded pile, the load that is required to pull out a pile which is completely embedded into the soil, that load is the uplift capacity of that pile. Okay, so uplift capacity. And why it is required? See, in case of transmission towers, okay, so transmission towers like this, suppose these are transmission towers, suppose it is a transmission towers, and at the base of the transmission towers there are pile caps, and underneath there are piles. The transmission power towers are generally supported on pile foundations, so like this. Okay, these are piles. And suppose due to wind load, suppose due to wind and earthquakes, what will happen is, what will happen over here is that suppose wind is coming from this direction. Okay, and it will try to rotate into in this direction, due to which these piles these piles will try to rotate in this direction, and due to which these piles will tend to move upward, right? Suppose this is the ground surface, and if this transmission tower tends to rotate in this direction due to wind, these piles will also tend to rotate in this direction, due to which this pile will tend to move upward. Okay, and these piles will tend to move downward because this pile will tend to rotate in this direction, and that is why these piles will tend to move downward. Okay, so that is why we need to find out the uplift capacity. Okay, yeah, for this type of scenarios, we need to find out the uplift capacity. So gross uplift capacity we need to find out. For this particular question, I have been asked to determine the gross uplift capacity of the pile. So what is the gross uplift capacity of the pile? Well, the gross uplift capacity of the pile can be determined by PUG. Okay, PUG. This is the gross uplift capacity, which is equal to PUN plus W. What is PUN? It is the net uplift capacity. And this W, what is W? W is the weight of the pile, because weight of the pile will also will also contribute to the uplift capacity, right? Because weight is acting downwards, all right, and it is trying to, it will try to counteract the load that tries to, that tries to pull out the pile. It obviously will try to counteract the load that will try to pull out the pile. So this is the W is the weight of the pile. Uh, so we need to find out PUN and W in order to find out the gross uplift capacity. So what is PUN? So this is a clay soil, right? In the question, the soil is clay. So for clay soil, PUN is equal to alpha dash CU P, that is the perimeter of the pile, and L, that is the length of the pile. Okay, CU is the undrained cohesion and alpha is the adhesion factor. Okay, now alpha dash, that is the adhesion factor. It depends upon undrained cohesion and also the type of pile. Okay, so alpha dash is equal to 0.9 minus 0.00625 CU. This one is for cast in situ pile. Cast in situ pile and undrained cohesion of the soil in which the pile is installed, it should be less than 80 kPa. Okay, and there is another equation, the another the alpha, where alpha dash is equal to 0.4. In this particular case, it is also cast in situ pile, but the undrained cohesion here is greater than 80 kPa. Okay, and in case of pipe pile, that is hollow piles, alpha dash is equal to 0.715 minus 0.0191 Cu. Uh, this equation is used when the undrained cohesion of the soil in which the pipe pile is installed, it is uh, less than equal to 27 kPa. Okay, and another equation is another alpha dash is zero point 0.2, and when the Cu is greater than 27 kPa. These two are only for pipe piles. Okay, so here the pile is a solid pile. So, and also the cohesion, how much is the cohesion? Undrained cohesion is 100 kPa. So 100 kPa, that is greater than 80 kPa, so it is 0.4. And in the question is, it is also given, I believe, in the question the adhesion factor is also given, which is also 0.4. Okay, so now we need to use this we need to use we need to use these values. We need to put all the values of all the parameters into this equation to find out PUN. Okay, so let me add a slide over here. So PUN, So PUN. Okay. How much is PUN? What is the formula for PUN? PUN is alpha dash Cu P into L. PUN means alpha dash Cu P into L. Okay, so alpha dash is how much? Alpha dash is how much? So alpha dash is 0.4, and underend cohesion, how much is the underend cohesion? It is 100 kPa. And what is the perimeter of the pile? It is pi into d, that is pi circumference of the pile, which is pi into d is the diameter of the pile, which is how much? It is 0.5 meter. And length of the pile, L is how much? It is, let me check once. The length of the pile is 20 meter. Okay, so L is 20. If you calculate this equation, you will get the value of PUN to be 1257 kilonewton. Okay, so we have found out the value of PUN, and now we need to find out, we have found out this term, value of PUN. We need to find out this W. We need to find out W, and after that we need to add both the terms in order to get the gross uplift capacity. Okay, so we have found out this PUN. We need to find out W. Okay, that is the weight of the pile, and after that we need to add both the terms in order to find out the gross uplift capacity. Okay, we have already found out this term. We need to find out weight of the pile. After that we need to add both the terms in order to get the gross uplift capacity of the pile. So what is the weight of the pile? We know the unit weight of the concrete. How much is the unit weight of the concrete? It is 24 kilonewton per meter cube. And now if we just multiply the unit weight of the concrete with the volume of the pile, we can we will easily get the weight of the pile. So weight is how much? We need to find, we need to just multiply the volume of the pile with the unit weight of concrete, right? So what is the volume of the pile? How much it is? So area into length. Okay, so how much is the area? Pi by 4 into d square. How much is the d? It is 0.5 square into length. How much is the length of the pile? It is 20 meter. And what is the unit weight of concrete? It is 24, right? 24 kilonewton per meter cube. Now if you calculate this, you will get the value of W to be how much? 94 kilonewton. Okay, 94 kilonewton. Now you need to add both the terms, this term and this term, that is P1 and W. If you add both the terms, you will get the value of gross uplift capacity. So PUG is equal to PUN plus W. So PUN is how much? PUN we have found out, it is 1257 kilonewton, and W is 94 kilonewton. So 1257 plus 94, and this will come out to be 1351 kilonewton. So this is the uplift capacity of the pile. Okay. So if you have any doubt in this regarding this problem, please let me know. You can also let me know the doubts via email, and also you can write your doubts in the chat box. Okay, and in the discussion forum also. Uh, please go through this problem once. I will resume this session after 5 minutes. So I hope you have all understood this problem. So let me now proceed to the next one. So this is the fourth problem. So let me first read out the problem. Determine the lateral deformation at the top, that is at z equal to 0, of a solid free-headed pile. We need to determine the lateral deformation of the pile head, okay, of a solid free-headed pile subjected to horizontal load of 165 kilonewton at the top of the pile, that is at the ground level. Use Rees and Matlock method, okay. So here in this problem we need to use the Rees and Matlock approach. In the first problem, I believe, that is in this particular problem, in the first two problems, we have used the Hetteny approach, okay. In the Hetteny approach, the subgrade modulus remains constant throughout throughout the depth, okay. Throughout the depth of the pile, the subgrade modulus, the horizontal subgrade modulus remains constant in Hetteny approach. But in recent Matlock approach, so this is the subgrade modulus, the horizontal subgrade modulus. This is constant throughout the depth in case of Hetteny approach. But in case of recent Matlock approach, uh, the horizontal subgrade modulus varies. It varies linearly with depth. Okay. So let me see all the other data that are given, which are given in this question. So diameter and length of the pile. So diameter of the pile is 0.5 meter and length is 20 meter. So and KH varies linearly with depth. The flexural rigidity of pile, that is EPIP, is 45,000 kilonewton meter square. And this one, eta H, this one is how much? It is 1250 kilonewton per meter square per meter. The coefficients AY and BY at Z, that is at the top of the ground surface, Z by T is equal to 0. So it is how much? So the coefficients are 2.435 and 1.023. We can also determine the coefficients from the chart. I will show you how. So before solving the problem, let me just present a brief about the recent Matlock approach. So recent Matlock approach. Okay. In case of recent Matlock approach, KH varies linearly with depth. In case of Hetteny approach, KH remains constant throughout the depth of the pipe. Okay. And how the KH varies? KH is equal to eta H. What is eta H? That is eta H, which is given in this question. In the question, it is 1250 kilonewton per meter square per meter. What is K in eta H? Eta H is the coefficient of subgrade reaction. Okay. It is a modulus of subgrade reaction. Okay. So eta H, let me view the slide once. Let me refer the slide once. So this is how it varies. Okay, see this particular equation. Okay. So so now let me just go back to the problem. Let me just solve it. So before solving, here in the problem, we have been asked to find out the lateral deformation. Okay, so lateral deformation due to the horizontal load H, there is a equation given by Rees and Matlock. So that equation is y is equal to H into T cube divided by EPIP, okay, into AY. It is the coefficient. Okay, this equation, it is for horizontal load. Okay, and if a moment is acting, in that case, m0 t square divided by EP, IP and by. Okay, and in this particular question, since no moment is acting, okay, since there is no moment, there is no need to consider this part. Okay, m0 is equal to 0. Okay, so we need to consider only this part. Okay, so what is t? We know the value of H, that is the horizontal load that is acting. We know the EP, that is the flexural rigidity of the pile. So we need to determine the value of T, and from the chart we can easily get the value of AY, and also the coefficient. The value of coefficient AY is given in the question, I believe. AY is already given. AY and BY for Z is equal to 0. Z means capital Z means small z by t. Small z by t. Okay, small z means the depth. And what is t? T is the relative stiffness factor. I will show you what is t. Okay, so this is the equation. So we need to first find out the value of t. So t is the, what is t? T is the relative stiffness factor, and relative stiffness factor is given by root 5 EPIP divided by eta H, that is the coefficient of subgrade reaction. Okay, using this equation we can find out the value of t. Okay, so let me use this equation to find out the value of t. So t is equal to EPIP divided by eta H to the power 1 by 5. Okay, EPIP, how much is EPIP? If it is given in the question, so the flexural rigidity EPIP is 45,000. EPIP, let me write down all the data that are given in this question. So EPIP is 45,000 kilonewton meter square. Eta H is how much? It is 1250 kilonewton meter square per meter. AY and BY, I will write them later on. What is the horizontal load? H is 165 kilonewton. And what is the diameter of the pile? Diameter is 0.5 and length is 20 meters. So diameter is 0.5 meter and length is how much? It is 20 meter. Okay. So now we need to use these, use all the data to find out the value of T, which is the relative stiffness factor. So EPIP, how much is EPIP? EPIP is 45,000. So 45,000 divided by eta H, how much is eta H? It is 1250. So 45,000 divided by 1250 to the power 1 by 5. Okay, if you solve this, if you calculate this, you will get the value of T to be 2.05, and the unit is in meter. Okay, the unit is meter, 2.05 meter. And one thing, I must mention that this Matlock and Rees approach, is applicable. And one thing I must mention that this Matlock and Rees approach is applicable only for long pile. And what is the long pile? In case of long pile, Z max is greater than 4 or 5. Okay, 4 or 5. So what is Z max? Z max is equal to L by T. L is the length of the pipe and T is the relative stiffness factor, that is this, okay, T. So now we need to check once the value of L by T, okay. So before proceeding, we need to check once what is the value of L by T, okay. So L by T, the length of the pile is how much? It is 20 meter, and T we have found out what is the value of T, it is 2.05 meter. So 2.05. Now, how much is L by T? It will come out. It comes out to be 9.8, and it is much greater than 4 or 5. Okay. So that means it is a long pile. Okay. And we can use matlock and Rees approach. Okay. So now we need to determine the corresponding lateral deflection. So what is the formula for a lateral deflection? This one. HT cube divided by EPIP AY. Let me write it down once. So formula for lateral deflection due to horizontal load H is equal to HT cube divided by EPIP into AY. AY is the coefficient, okay? At Z is equal to 0, that is at the ground surface, okay? So now let me just put all the values of all the parameters into this equation. First of all, let me put all the parameters into this part, okay. So what is the value of H? That is the horizontal load that is acting. It is 165 kilonewton. So H is 165 kilonewton. And what is T? That is the relative stiffness factor. It is how much? It is 2.05 meter. Okay, 2.05 cube. Okay, and how much is EPIP? How much is EPIP? That is the flexural rigidity. It is 45,000. Okay, so 45,000. And AY, we need to AY, the coefficient of AY is already mentioned in this question. It is 2.435, but from the chart you can also find out. So for the Z is equal to 0, that is at the ground surface, AY is 2.435. Okay, it is also mentioned in this question. AY is 2.435. So you can write it down. AY is 2.435. Now, if you calculate this, you will get the value of Y. Y will come out to be 77 millimeter. Okay. So this is the value of lateral deflection of a pile if you solve this problem using Rees and Matlock approach. Okay. So this is the answer. Let's go through this problem once. So now let me proceed to the next problem. So what is the next problem? The final problem. Determine the lateral deformation at the top, that is at Z is equal to 0, if the pile is a fixed headed pile under the same conditions described in question number 4. So in question number 4, the problem was, what was the, in this particular question, the pile was free headed. Now we need to find out the lateral deflection of a fixed headed pile. Okay. Similar type of question, all the data are same, but here there is a fixity, that is the pile is a fixed headed pile. Okay, and we need to find out the corresponding deformation of the pile head, okay, under 165 kilonewton horizontal load. The load is also same, okay, under the same conditions described in question number 4. Okay, so as we have discussed in earlier two questions, in question number 1 and question number 2, what happens in Hetany approach, actually what happens is Hetany approach is that uh, in order we consider the fixity of the pile head by introducing a counteracting moment, right? So here also we will also do the similar thing, okay. So so due to fixity there will be a counteracting moment, all right. Similar thing happens over here. See, suppose you have a pile cap like this. Suppose we have a free-headed pile like this, and if you apply a load over here, it will deflect like this. Okay, this is the original position, and this is the deflected. Okay, so now if this is the free-headed pile. Now, if you introduce a cap like this on top of the pile, that is a fixity, it will not deform like this, okay? It will not deform like this. Instead, there will be a counteracting moment, okay? It will try to deflect the pile like this, okay? Obviously, it will try to resist this deformation, okay? So, due to which there will be a counteracting moment which will try to resist this deformation. And here also we first we need to consider the pile to be free-headed. We need to find out the free-headed. We need to find out the deflection of the pile head, considering the pile to be a free-headed pile, and after that we can introduce the fixity by by introducing a counteracting moment. We need to find out the deflection due to that counteracting moment, and we can subtract the deflection from the free-headed deflection, and after that we can get the net deflection. Okay, so in the similar way that we did in the previous two sums, we will follow the similar process in this sum also, for this sum also. So here in recent MATLAB process, the counteracting moment is given by, that is the m0, that is the counteracting moment due to the fixity. It is given by minus 0.93 ht. Okay, h is the horizontal load and t is the relative stiffness factor. So 0.9 ht minus 0.9 ht. Okay, so how much is so how it in m0 comes out to be, h is how much? It is 165 kilonewton. It is already given in the question. It is 165 kilonewton. And t is how much? T we have calculated. uh, T we have calculated using this equation, and T is how much? It is 2.05 meter. So 165 into 2.05, and if you calculate this, you will get the value of m0 to be minus 314.6 kilonewton meter. Okay, this one. Now we need to find out the deflection due to this counteracting moment m0. Okay, so deflection due to moment is given by, that is due to m0. There is the equation given by Matlock and Rees, minus m0 t square divided by EPIP by. Okay, we know the value of m0, we know the value of t, we know the value of the flexural rigidity, that is EPIP. We need to find out this by. By is the coefficient. We can use the chart. We can use this chart to find out value of by. Since the head of the pile is at the ground surface, so for z is equal to 0, the corresponding by is this 1.023, and this is also given in the question, I believe, 1.023. See over here. Okay, so everything is given, everything we so so all the parameters that we need to solve this equation, we have all the values of all the parameters that we need to solve this equation. So now let us just put the values of all the parameters into this equation. So how much is m0? M0 we have already determined. It is how much? It is minus 314.6. So m0 is minus 314.6. And how much is T? T is the relative stiffness factor. It is 2.05 meter. So 2.05 square divided by EPIP. How much is EPIP? That is the flexural rigidity is how much? It is 45,000. Okay, 45,000. And how much is By? By from the chart, this value 1.023. 1.023. Now, if you calculate this, you will get the value of y. So, value of y comes out to be, it comes out to be around 33.06 millimeter. Okay, this is due to the counteracting moment. Okay, in the opposite direction to that of the free-headed deflection. So, it is around 33 millimeter. Okay. So now we need to find out the net deflection. So net deflection is how much? Deflection due to free-headed minus deflection due to M0. Okay. So what is the free-headed deflection? We have already found out over here. So free-headed deflection is 77 millimeter. Okay. So 77 minus what is the deflection due to M0? It is 33 millimeter. Okay. 33 millimeter. So net deflection is around 44 millimeter. So this is the answer. So the net deflection is around 44 millimeter. Okay, so that is all for today. So that is all for today. I hope you have all understood these problems which I have solved today. If you have any doubts, you can mail me personally. You know my mail IDs, and mail IDs are also given in the YouTube description boxes in each and every videos. You can also write down in the NPTEL forum. Okay, so that is all for today. See you in the next session. Good night.